My name is Muzio. I'm a postdoc at Penn State, and today I'm going to be telling you about work we've been doing on the Askaryan Radio Array, or ARA. So today, astrophysics has entered what's been called the multi-messenger era, and this is just to say that today on Earth we have lots of different experiments that measure astrophysical events and environments in different ways, particularly with different particles. Some detectors are measuring gravitational waves, while others measure cosmic rays, neutrinos, or gamma rays. These are kind of the big four. If you measure all of these different kinds of particles from a single source, you can actually learn a lot more about that source than you would through just one of them. Each of these messengers or particles has their ups and downs. In particular, gravitational waves, it's hard to tell exactly what direction they're coming from. Cosmic rays sort of meander through magnetic fields in the universe and take a very long time to get to Earth. Neutrinos don't interact much, and so they're very, very difficult to detect. And gamma rays have interactions as they move through the universe, and so very often they end up being absorbed before they ever get to Earth. Now, this thing that makes neutrinos so hard to detect actually also makes them a very unique messenger, because not only will they travel in straight lines and at nearly the speed of light, they'll also come from environments that are inaccessible through the other messengers, namely because they don't interact much and they won't lose energy as they propagate to Earth. And so this allows us to study, use neutrinos to study not only multi-messenger kinds of environments, but also environments that are really far away in the so-called high redshift universe. They also can probe extreme astrophysical environments where other messengers may never be able to escape. And we think that they can be used to actually discover the sources of the highest energy particles ever observed, ultra energy cosmic rays. And if you do manage to observe neutrinos at the very highest energies, you'll actually be able to learn something about particle physics beyond the reach of accelerators here on Earth. And so neutrinos are really providing a unique window into the high energy universe. So how do you actually see them? The problem is that neutrinos at the highest energies are really rare. And so you need an enormous detector to actually be able to see them. Now, when neutrinos pass through ice, once in a while, they'll have an interaction. They have an interaction with an atom in the ice. They will produce a particle shower, and this particle shower will produce radio emission that we sometimes call Askaryan radiation. The really nice thing about radio waves is that they travel kilometers in the ice. And that allows you to place a few radio antennas inside of the ice and actually probe a very large volume. And so this is exactly what ARA has done. And so our detector ends up being enormous, roughly on the order of 10 cubic kilometers. So ARA itself is, of course, located at the South Pole, very near Ice Cube Lab. And it's made up of 5 independent stations that are each placed about 2 kilometers apart. And each of these stations has 4 strings of radio antenna that are embedded deep into the ice to capture those radio waves that are emitted when a neutrino has an interaction. And in particular, the 5th station of ARA has a unique extra string that's called the phased array there at the center. And this is an important piece of the 5th station of ARA because it allows us to detect very, very weak signals in an efficient way. So ARA has been running for about 10 years, and we've done a lot of really exciting science along the way. In particular, we have set the strongest limits on the neutrino flux at ultra-high energies from any in-ice radio detector to date. And in particular, with the addition of the phased array on the 5th station of ARA, we've also been able to demonstrate how you can do a very low threshold search for neutrinos and really increase the amount of science you can get out of the data. Additionally, we've looked for neutrinos that are coming from gamma ray bursts, and set quite stringent limits there. And we've also observed a solar flare that's allowed us to validate the fact that we can point back to a source of radio waves from a non-anthropogenic source in particular. Of course, we really want to understand our detector, and our detector is really the ice at the South Pole. And so we spent a lot of time trying to study the ice and its properties, and that's going to be vital for the next generation of experiments. But it's also of interest to the glaciological community as well. Now, ARA is not done yet. We've accumulated 25 station years of data, and we haven't analyzed all this data. So on the horizon, the very near horizon, we have a few very exciting studies coming up, including a novel template search for neutrinos in our data that should be able to demonstrate how powerful that technique can really be. We're also performing a neutrino search using the fifth station of ARA, which is in a configuration like the next generation of detectors. And so we're really pioneering how that analysis can be done. And that next generation of detectors includes IceCube Gen 2 radio. And finally, we are analyzing our full livetime, our full data set across all stations so that we can set the record again for limits on the diffuse neutrino flux at ultra-high energy. So please stay tuned for that. And thanks so much for listening. I'm really looking forward to hearing about all the science going on at the South Pole. Thanks.